Assalamualaikum warahmatullahi wabarakatuh to all. Today, I'm Ian Hafiz.
And I am Amir Haikal.
We'll be discussing about man-made satellites. There are two main topics in this chapter. The first part is about orbit of satellites, and the second part is about geostationary and non-geostationary satellites. Now, let's discuss our first subtopic, orbit of satellites. As we all well understand that the satellites are located to improve human lifestyle for communication such as making phone calls, watching satellite television, there are communication satellites and remote sensing satellite. Next, Earth observation for weather forecasting. To track storms and pollution, there is weather satellite. Then for navigation, there's Global Positioning System GPS satellite, which is used in map and navigation like Google Map and Waze. Then for scientific investigations, there is navigation satellites such as the Kaguya satellite. Then for military, which is spying, there are drone satellite, ground satellite, and polar satellite. And lastly, for satellite photography, there are geostationary satellite GEOs. Can anyone tell me what was the first man-made satellite? Yes, Sputnik 1 launched by Russia in year 1957. Some examples of satellite are, the first one is the International Space Station, ISS. This satellite can be seen from the Earth as the distance is short, which is 408 kilometers. The second one is Malaysia East Asia Satellite, which is known as MEASAT. This satellite is difficult to be seen as the height from the Earth is 55,786 kilometers. There are essentially three types of Earth orbits. The first closest to the surface of the Earth is low Earth orbit, which is LEO. The movement of a satellite around the Earth is fixed in either a circular or an elliptical orbit. In LEO, there is communication satellite. Then, in medium Earth orbit, known as MEO, it includes the navigation satellite, which is designed to monitor a region. Then, in high Earth orbit, there are weather satellite and some communication satellites. Satellites move at a certain height h and suitable linear speed v. From previous learning, we have learned that the formula for centripetal force is given by F equals to mv squared over r, and the formula for gravitational force in Newton's universal law of gravitation is given by F equals to g capital M m over r squared. Now, what is the relationship between these two formulas? If a satellite moves in a circular orbit, it will experience centripetal force, which is the gravitational force. In other words, centripetal force is equal to gravitational force. mv squared over r equals to g capital M m over r squared. Then, let's simplify the formula. We will get v squared equals to gm over r. So, the linear speed v of a satellite is v equals to square root gm over r. Now, let's try to understand one example from textbook page 104. To calculate linear speed of man-made satellite, it is important to determine the sufficient linear speed for satellite to enable it revolves in its respective orbits. Before that, let me give some examples on application that we usually use relating to the linear speed. Now, the question is, what is the linear velocity v of this GPS satellite? Let's consider a global positioning system GPS satellite. Its altitude or height from Earth's surface is equal to 20,200 kilometers. Using the equation v equals to square root gm over r, where r equals to r plus h, so its linear speed is v equals to square root gm over r plus h. The radius of orbit, which is the small letter r, is 6.37 times 10 power 6, which is the radius of the Earth, plus 2.02 times 10 power 7. We will get the radius of the orbit is 2.657 times 10 power 7 meters. So, the linear speed is v equals to 6.67 times 10 power negative 11, which is the gravitational constant, times 5.97 times 10 power 24, which is the mass of the Earth, divided by 2.657 times 10 power 7 meters. Square root the answer, you will get 3.87 times 10 power of 3 meter per second.
Okay, what will happen when linear speed of the satellite becomes less or decrease? Okay, let's say a given linear speed of a GPS satellite is 3.87 times 10 power of 3 meter per second. If this linear speed becomes less, what will happen? It will fall to lower orbit and revolves around the Earth until it enters the atmosphere. As it enters the atmosphere, it will be moving against the air resistance. Therefore, it will generate heat and burn. Now, we move to our second subtopic, geostationary satellites, GEO and non-geostationary satellites. These satellites are in certain orbits depending on the mission of the satellite. The distance between the satellite and the Earth's surface will determine how quickly the satellite moves around the Earth. Geostationary Earth orbit, GEO satellites, are in geostationary Earth orbit. Geostationary at a high altitude, usually 3.57 times 10 power of 7 meter away from the surface of the Earth. So, what are their functions? It used for communication satellites to monitor severe weather conditions such as tornadoes, flash flood, and hurricanes. For example, MESAT. Non-geostationary Earth orbit geosatellites are in lower or higher orbit of geostationary Earth orbit. The orbit is positioned at low altitude between 700 until 1,500 km and for MEO at 10,000 km away from the surface of the Earth. Uses for Earth imaging, for surveillance, data gathering for GPS, and for satellites. The example are CubeSat, RASAT, PP, and ISS. Geostationary satellites. Why is it called geostationary? Because it appears stationary with respect to the Earth's surface. It always above the same geographical location, which means the satellite will orbit around the Earth in the same direction as the direction of the Earth's rotation, at the same rate of the Earth's rotation. In example, the orbital period T is equal to 24 hours. Now, we move to the advantages about geostationary orbit satellites. The average lifespan for a geo satellite is approximately 8 years, which made it can hold longer in space. And the disadvantages about geostationary orbit satellites are the greater height of the orbit, hence transmission losses will be bigger when compared to LEO or MEO. The satellite is more costly to install because it has greater height from the Earth's surface. And lastly, long path length introduces delays. Okay, now let's look at one example on how to use the formula for orbital period. T is equal to 4 pi squared r cubed divided by capital Gm in finding orbital radius of geostationary satellite that orbits around the Earth. For geostationary satellite, orbital period is equal to period of Earth's rotation, which is 24 hours. In this chapter, we must remember G is equal to 6.67 times 10 power of negative 11 Newton meter squared per kg squared, and M is equal to 5.97 times 10 power of 24 kg. And for T, we must convert hours to second in SI unit. 24 hours times 3,600 seconds is equal to 8.64 times 10 power of 4 seconds. And lastly, we put all the values into the formula. 8.64 times 10 power of 4 seconds is equal to square root of 4 pi square r cubed divided by 6.67 times 10 power of negative 11 times 5.97 times 10 power of 24. Then we'll calculate it, and the final answer we will get r is equal to 4.23 times 10 power of 7 meter. Next, we move to non-geostationary satellite. Non-geostationary Earth orbit geosatellites are in lower or higher orbit than geostationary Earth orbit. Non-geostationary satellites above different geographical location at different time, which means it will not need to orbit around the Earth in the direction of the Earth's rotation. The orbital period T is shorter or longer than 24 hours. And the advantages about non-geostationary orbit satellites are very small, simple, and low cost for data transmission. It has minimum quality delay, and it is advantages about non-geostationary satellites. The average lifespan is approximately only 5 years. Okay, lastly, I want to give you some information, which is The first man-made satellite to orbit the Earth was named Sputnik. The first living creature in space was Laika. The first rocket to the moon carried a red flag, and the first photograph of the far side of the moon was made with a Soviet camera. If a man orbits the Earth this year, his name will be Ivan, by John F. Kennedy. I think that's all from us. Thank you.